So Matt Lipson is our first speaker for this session. And he will talk about Urban-PLUMBER and Bureau urban updates. That's well.
Great. Thanks very much for having me here. Yeah, so as from the talk title, you can see that I'm trying to cram together two talks. So I do apologize for that. The first is the work at the Bureau of Meteorology on urban modelling, and the second is Urban-PLUMBER, which is following on from Gab's presentation, and I'm working there with Gab and Sue Grimman and Martin Best and many co-authors to undertake a similar analysis across urban sites. So at the Bureau, we're interested in urban modelling, high resolution urban modelling. Number one, because people live in cities and infrastructure there's a lot of infrastructure in cities, so impacts are often felt in cities. So it's important to understand extreme weather events in cities, but also because the urban surface can interact with regional weather to produce or intensify some particular local scale weather interactions, urban heat island, intensification of precipitation. Obviously, there's interactions with winds and fog and air quality that are important in urban areas. So an Australian urban scale model that we're developing will provide enhanced NW or numerical weather prediction capability at the city scale, and also be used by downstream models for impacts assessment. So just a reminder that at the Bureau, when we talk about ACCESS, we're talking about plus joules. Doesn't have cable in our ACCESS models. So we're using 13 and the latest regional atmosphere and land configuration. And these results or configurations that I'm presenting are numerical weather prediction models, but we're also running seasonal and climate configurations. So my focus again is high resolution regional model configuration and evaluation, land cover, urban morphology development. And on that last point, this is work that I've been doing for the last 12 months or so to try and improve the characterization of Australian cities in our models. So on the far left, these are all plots of Sydney, and on the far left, this is what we currently use, IGBP, for our operational models. And that was imaged back in the early 90s. So our city shapes have changed since then, but also they're represented in the models as being 100% impervious. So essentially a big concrete slab across all our cities. So that's not very realistic for Australian cities, which are quite low density cities, and the vegetation is quite important. So we've been looking at a series of globally available data sets and comparing them against a very high resolution building resolving data set on the far right that we have for Sydney, and working out which of these global and openly available data sets can we use in our configurations. And we're settling down on world cover, which is a ESA product at 10 meter resolution, which has a good result for cities, we're finding. So we've configured some high resolution models and undertaking some analysis. This is an example over Sydney, and Sydney is quite an interesting case. It's a coastal city affected by sea breezes. It's surrounded by mountains, so it has some interesting interactions with the topography and the ocean, and we are starting to see that our high resolution models are providing benefit in these complex cases. But that very high resolution work is also informing what we're doing at larger scales. So this is a new NWP model called ACCESS-A that we've just finished or signed off on the configuration for, which is across Australia, 1.5 kilometer resolution. So it's a big model, and we have characterized cities using world cover, and we're starting to see some benefits there at the what we call what I would call lower resolution, but 1.5 kilometers is still obviously very high resolution. So yeah, we certainly do see benefits in cities at different resolutions. And at the other end of the scale, going very, very high resolution, this is a project we're involved in, the Paris Research Demonstration Project, NWP at 100 meter scale. So this is very computationally expensive, and this is where we think some of the parameterizations should really be breaking down the way that we represent cities, the assumptions that we have for land surface schemes in general. We're testing the boundaries here, but the point that I want to make is we can better characterize the cities from our default global data sets, and using world cover over Paris, for example, we get a nicer picture that is resulting in what we see as better results for 2-meter air temperature, say. And when we compare with the other groups that are participating, this is the first plot that's come out of the intercomparison. It's very, I find it very hard to read, but apparently we're doing well in that jumble of lines. So we think that the characterization of urban areas is providing benefit. But there are still ongoing issues that we're continuing to find in our operational models, particularly for urban areas. So this is, well, Luigi mentioned the leaf area index. We use Modus to configure our leaf area index, and we've discovered that the leaf area index in urban areas is set to 0 in our models. So it doesn't matter if we're better representing the vegetation components in our urban areas if they have no leaves. And also on the left there, we have the ACCESS soil moisture remote sensing product, which we use to initialize our models. This is during the Black Summer bushfire period, and you can very clearly see Sydney and Melbourne. These are spuriously wet signals caused by the impervious areas of urban areas. The microwave sensor sees that as being a very wet signal. But this is, and so that's how we initialize our model. It's very, very wet in cities, which is just not correct, and has significant impacts, can affect surface air temperature, humidity, obviously. And so this is something we're also working to correct. But I just want to point out that it seems that urban areas are often a blind spot for the land surface community. And also the weather and climate communities, to be fair. But these issues have been, they're long-standing issues, which we're now working with Luigi and Chris Rudiger's group to help resolve some of these issues. So in summary, we use plus joules, work to better characterize Australian and international cities. There are some ongoing issues, and we've developed a range of resolutions. And these configurations and new land cover data sets are open to the ACCESS community, and we're happy to collaborate on anyone who wants to work with these models. So now quickly jumping to Urban-PLUMBER. 20 sites, 30 models. It's continuing out of Gab's work, so I won't go into the methods, but one of the first problems that we had in this project was that there's only one, from what I understand, there's only one urban site in all of FluxNet. So we had to work with and talk to a lot of observational groups and convince them to open their flux tower data, release it openly, apply quality control and gap filling processes. And that's the first big output of this project is a new collection, a harmonized collection of urban flux tower data sets across the world. And they vary greatly in their urban types, from very low density to very high density sites. So a really useful data set for the urban community to start to evaluate models in the future. For the ACCESS community, there are 5 parameterizations that are useful. 5 parameterizations that are in the project, I should say. So cable is. We wanted to include some land surface models that didn't have an urban parameterization. So we started to understand when is it important to include an urban parameterization. So we have cable in there. We have joules, 1 tile, 2 tile, and Marusa schemes. And we also have UCLEM, which is part of the CCAM model. So cable UCLEM. And this is the sort of the plumber style plots, although it's obviously a little bit different, where we compare model results against the different benchmarks. And what I've done here is along the x-axis, where we have the models, is just generally have an increasing level of complexity from left to right, so that we have non-urban models, or with no urban representation, 1-tile, 2-tile, urban canyon models, and then quite complex building resolving models on the far right, and some ensemble mean time series on the very far right. And essentially, what we're showing here is different benchmarks. I think the one to keep your eye on is the 3-variable nonlinear out of sample regression that is also used in Plumber 2015. And when a model beats that benchmark, it gets a little color indicator. So dark green means it's beaten the 3-variable benchmark. So what you can see here for sensible heat and for latent heat is that quite a lot of the models are getting that green tick. And so quite a lot of the models for these 20 urban sites are beating the benchmarks. If I highlight the ones that are of interest for access community, we have cable. Now that is not beating the benchmark not beating any benchmarks in latent heat, and it's just beating a simple physically based benchmark in sensible heat. But these are the more complex or urban LSMs that include an urban representation are doing quite well comparatively. Particularly the Joules set of models is one of the better performing models in the comparison project. When we split things out to each site, so again, this is the color indicator of how many benchmarks were beaten, and we go from very low density to very high density sites. And you can see for cable, it really starts to drop off quite as the site becomes more urbanized and starts to fail to beat the benchmarks. But the Joules ones are able to do well throughout most of the range. And this is why it's pretty clear why for latent heat flux, at least, that if we have the evaporative fraction across an increasing site urban fraction along the x-axis, so very low density urban sites, very high density urban sites, the green is the non-urban cohort of models, and we start to see, well, initially it's slightly low on the evaporative fraction compared to the black, which is the observations. And as we progress through into denser and denser sites, we do see that there's far too much evaporation, far too high latent heat flux compared to observation. But interestingly enough, we even the urban schemes at the very high fractions have a low evaporative fraction compared to observations. So I'm just going to skip through this because I'm running out of time, other than to say that the long wave radiation flux is performing more poorly than the latent sensible heat flux, which we found interesting. So in summary, LSMs are often doing better than the benchmarks at urban sites. The 1-tile, 2-tile Marusa schemes are performing well compared to other LSMs in the project, and Joules outperforms cable even at lower urban fractions. In general, the benefit of an urban scheme becomes apparent at about 30% urban fraction, and simple and mid-complexity urban schemes can perform well if they have reasonable hydrological and behavioral representations. Phase 1 results is soon to appear in QJRMS. Thank you very much.
Thank you, Matt, for great presentation and comparison. You showed a lot of comparison based on how the surface fluxes are around the canopy, but in the start of your presentation, you also noted that there is interest in impact assessment within the canopy. Do you have anything, can you add on that, like how flux also from that perspective?
Yeah, it's a really important point, and this evaluation that we're undertaking is not assessing the conditions within the canopy where people are. And so a lot of these models were designed for the large scale, mesoscale simulations where they only care about the surface fluxes. But we will need a different set of observations and a different evaluation process to really assess how these models are performing where people are. They're probably not performing very well.
Can you please just unmute yourself and ask your question?
Sorry, it's just a bit hard to hear.
Oh, it was asking if there was any online
Oh,
question.
okay.
Any investment from the room.
Matt, I assume this is keeping to what's in the paper rather than what you suggested was a really good idea to me in terms of the way the 0 to 1 range includes or does not include the land model being benchmarked.
Yes, that's correct. I haven't updated the plots with the with that suggestion yet. But it'll be interesting to have a look at.
Really interesting. Thanks for your suggestion. That's going in the paper.
Great.
Lovely stuff, Matt. At what point do we quit trying to physically model this stuff and move to a machine learning type approach to capture the essence of the urban? Because you're mostly interested in forecasting on timescales of days, and what's your thought about replacing the physical parameterizations with something embedded in machine learning?
Yeah, I mean, I would have thought there would be good application at the weather scale. Obviously, at the climate scale, it's a different story. I did suggest, or we did suggest this to Martin Best a few days ago to look into this a bit more, but he strongly pushed back on a machine learning approach for representing the surface energy balance, for example. So yeah, I'm I'm not sure.
I'll
I think
I'll see him in a couple of weeks and I'll push harder.
Let's move to the second speaker. Thank you, Matt.